All right. We have a couple of questions online I'm going to start with. So let's thank everybody again for their talks. There was a question that was for the gecko surfaces, which was, is the material easily recycled or decomposed?
Interesting. It's actually kind of dexterous. Is that the right word? It's like you can stretch it. It's pretty stretchy. It won't rip, but it is kind of fragile. It doesn't decompose. Just cleaning it off might be a challenge.
Okay. And then for Cecily, we had a couple of questions. One of them was, can you, this is from Brad Jolliffe. He said, great talk and interesting results. Can you incorporate the stochastic effect of excavation of clods of regolith and introduction into the exhaust plume stream?
Ooh.
Should I paraphrase that maybe?
Yeah.
Yeah, so I think this is oftentimes we see in the Apollo videos, right, that there's chunks of material that get sort of pulled up and blown off, but it's fairly stochastic. So can you like sort of randomly introduce some larger clods?
I could. So as I mentioned before, an input to our model is an input to the simulation is the erosion model. So if there's some type of like probability of that happening that we could use, I could introduce it at that rate, but I can't use the simulation to determine when that break off would happen.
Yeah. Okay. Makes sense. Do we have any questions, Dr. Britt?
For Joseph, all the particles that you were using were within a factor of a couple, about the same size. If you're going to model macro asteroids and porosity, there's two critical things. The particle sizes are going to be multiple orders of magnitude different. Plus, it's going to be the really fine stuff that holds things together, which is something that Parks and others have shown. So I think it's really important to get both the micron size components in and the multiple meter size particles in. So you're talking 4 or 5 orders of 6, 7 orders of magnitude right there. So good luck with your modeling.
Yeah, thank you for that. Actually, it's an interesting thing you bring up. So the difficulty, if we were just using spheres, right? If we go back to before we started gluing particles together and we're just using our spheres for these models, the issue then becomes in the neighbor searching algorithm. So this is getting a little bit into the depths of the code, but if you have a very big particle and you have a bunch of very small particles that could come into contact with it, you need to make sure you have room to store all of those contacts or predict all of those contacts for this soft sphere method, right? And so suddenly you're doing these huge spheres searching for neighbors for all of these different possible sizes of particles that you could have. And that takes much longer than the increased time step that we need to model potential overlaps between a very large aggregate, like I've shown, and a very small aggregate. So this irregular particle method, this glued sphere method that we've taken, actually lends itself a little bit better to that sort of thing than the previous approaches might have.
Okay.
It's still difficult. It's still a tough problem. You're absolutely
I'm
right.
Sorry.
Yeah.
But I think that's really the driver, is the big stuff being stuck together with the small stuff. And the small stuff is really where all your forces are.
Yeah.
I also have a follow-up to that too. So
Well, if Jared's going to chime in real quick and then.
sorry, Connor. So one problem with it we've run into with our DEM simulations is, yes, the contact, you need a large time step for that. But if you zoom even further in numerically, small and large contact math, it just breaks down. A lot of time computers just won't handle it. Programs will just straight reject it. I completely agree with you, Dan. Yes, this is a huge problem and we computationally need to overcome it. But I'm just trying to point out it is a community recognized issue, and people try to get around it with particle scaling, mass size, and everything. And it's a mess. Oh, believe me, I know.
During those orders of magnitude. Did you have a?
Yeah. So Connor Westcott, Florence Space Institute. So someone who comes from a exclusively computer science background, why not go talk to us over there? We have a lot of algorithms that handle these large scale, orders of magnitude difference, doing it optimally and not just trying to brute force connections, even if we break it down into neighbor searches. So would that be something too that, Jared too also mentioned that struggles with that. Is that something that the community is interested in?
Yeah. Yeah, absolutely. And that's sort of where things are going actually is discussions with trying to pull computer scientists into it. The trick is that software developers are expensive and astronomers don't have a ton of money. So when we're trying to develop these codes, it becomes an issue of, how do we pay the people who have the expertise in this kind of thing? And so we get a lot of astronomers trying to write code as best as we can. So that's sort of where we end up with this kind of thing. But yeah, no, you're absolutely right. And computational methods are getting better and better for these kinds of things. And, there's a little bit of trickiness between, we're talking a lot about DEM codes, but, PKD-Grav, as I mentioned, is technically actually an n-body code. So it calculates gravity primarily. And so we're trying to mesh those two things together. And Cecily was showing her code, which is trying to mesh a couple of things together. And everybody's trying to get their code to do a lot of different things or, everything, which is even harder. Nobody really wants to do that. So it's sort of picking and choosing what problems you want to solve and then trying to take the best approach for that and working with the tools that we already have so that it's not so much work to develop something brand new from the ground up that's going to take 10 or 15 years that we scientists can't get funding for because we need to be doing science. So
Yeah, that's right. Thank you.
Yeah, I mean, it is a good point overall for the community, right? Is that planetary science is inherently an interdisciplinary field, but also there is a lot of work in granular mechanics in folks who do granular mechanics in other scales and other settings. So there's actually an AGU session about granular mechanics. There's a plug for that one if you want to submit an abstract to that. We have a bunch of AGU sessions that we could mention. There was one more question online for Cecily, again from Brad Jolliffe. For interaction of the low angle parts of the plume with the surrounding topography, does that introduce turbulence and particle-particle interactions? Is this aspect incorporated into the model?
No, so we incorporate kind of a global roughness scale at the surface by changing the height that we sample the pressure of the gas. So right now we're sampling at 5 centimeters above the surface. But we cannot do actual topography changes. Yes, exactly. You're hitting on everything on my wish list.
Yeah, Brad's asking the good questions. All right, we have like 1 more minute. Does anybody have a question for another speaker or some additional you want to say?
I do. I have a question for Chris. And your last slide, you showed the Mars rover. And so it made me think of, for your EDS apparatus, it made me think of like, okay, what kind of design considerations are you thinking of for like lunar silicate dust, plaid, CPX, what have you, as opposed for Mars where you're gonna have a lot of clays and a different charging of that dust. So if you can comment on that.
So that's a very, very good question. Admittedly, my focus has been very much on the lunar applications. That's where I started with this. That's what my background is in. My background is in mechanical engineering. So all the differences of geology and clays versus dust, I know enough to design my brush about. I know that's one of the things I have been thinking about is when we get to start doing these solutions for Martian cases, we open up the design space considerably. And that was one of the things that when we started on lunar dust problem, most of the solutions that we could try to look for are very limited. And like with the bio-inspired design approach with the gecko feet, that's a really good approach. We can use that without having to worry about atmospheric conditions. But once we have more, or the different conditions of Mars, that kind of opens things up. So I haven't had a chance to really look at what I would like to do. I really like the bio-inspired approach of seeing what nature does. They've been living on these planets in our solar system for a lot longer than we have, and they've kind of adapted to things. So I'd love to take a look at that problem. I have not yet, though, unfortunately. But thank you for the question.
Thank you.
All right. Well, thank you again to all of our speakers and our audience for great questions, both here and online.